this is going to be potentially utterly obscure to you, but maybe it's also going to make sense, because I'm not actually going to talk about pseudoholomorphic curves. I'm just going to talk about, if you have a fuzzy space, how do you count the number of points in it? And then the question is, and that fuzzy space is going to come, from things that I'm not going to talk about. So today we'll talk about approach number 2, in which that fuzzy space is somehow described in terms of finite dimensional reductions. And I'll sort of remind that language again. That approach sort of started, I think, in '96 with Fukaya Ono, which was eventually published in '99, and a number of people have felt the need to clarify things in different ways. And I think we're not at the end of this. So I'm probably going to do a little bit of a literature review on Wednesday. But there's a lot of political questions around that approach. In particular, should you be questioning papers that are published? And I want to talk about the mathematical issues, because there are mathematical issues, and so we should understand the mathematical ideas first. So our guiding question is always twofold, right? So if somebody tells you you have a compactified moduli space that you can somehow declare or define a virtual fundamental class for by means of perturbing a section, or approach number 1, we took an Euler class of that section. There's 2 questions to ask. One is, what is this section you speak of in abstract terms? And the other one is, what is that section you speak of in specific examples? How do you get it from pseudomorphic curve moduli spaces? And the reason we like the idea of these finite dimensional reductions is that we had already Fredholm descriptions of a moduli space, and those have finite dimensional reductions. And then when we're thinking about nodal curves, we couldn't quite pull off a Fredholm description except for a finite dimensional one, which came from this stabilized gluing. So somehow, analytically, this finite dimensional context seems to be the natural one, which leads us to a somewhat categorical form of the abstract section. So in our world here, that is going to be space. I've been wanting to call that U. So I would like to think of this as a section of an étal bundle, where, so there's something, this is a functor, S is a functor between categories U and E. And, let me not call this étal, because there's going to be one condition that's going to fail. And then my moduli space is going to be, taking the 0 set of this functor. If you think of it just as a map on the level of objects, you're going to get a whole bunch of objects, but then you need to quotient by the morphisms, which is what we call the topological realization. So, more precisely, so all of this on the level of object level has a nice smooth structure. So the objects of my bundle E is a disjoint union of some think of trivial bundles with fiber EI over a manifold UI. So my object space, the base U is simply these UIs. So these should be smooth manifolds. With the little caveat that Well, and so the UI are smooth manifolds, the E are finite dimensional vector spaces. And the funny thing is that we allow the dimension to vary. So the dimension or the rank of the vector space can be something finite. What we can fix is sort of the virtual dimension, also known as the index of my problem, which is the dimension of U minus the rank of the vector space. So we now have, thing is, right, so if the dimension of U goes up, then the rank of the vector space also has to go up, right? So these are very much only locally constant dimension. But we have sections locally SI, which, well, I'm going to keep calling them section, but really they're just smooth maps from the manifold to the vector space. Well, so S you can think of as sort of disjoint union of all these SI. Right? And if those were transversed to 0 here, then they would cut out a little submanifold in U of exactly this dimension. So, and that dimension is constant. It's kind of the virtual dimension of my moduli space here. All right. And so with that, I can understand what this description of the moduli space is. It's simply the, well, I can't yet. Sorry. I'm going to take all the 0 sets, and then I'm going to want to glue them together. So this is where I need to quotient out by something that I haven't talked about yet, which is what are the morphisms in this story. So, and that's something, so that's the big remaining question on the abstract level, right? And that ties in exactly with the big remaining question on the application level, right? Where do we get the morphisms from here? So somehow here the morphisms should come from overlaps, or the transition maps. So, each of these sections here describes a little piece of my compact moduli space. So each of them, that's what's called the finite dimensional reduction. And the question is, how do they get glued together by the analysis that we have, hopefully. So, well, let's see. Well, right, and then, okay, so back to this, right? So once you have a section, you would like an abstract theorem that says, oh, if I wiggle that section a little bit, I'm going to get a smooth manifold out that I can counter that has a fundamental cycle. So here is our sort of master regularization theorem for one bundle in finite dimensions in just one section. Right? So we would like a theory that essentially has a theorem like this. So we'd like, here you should, well, this is true if E is a finite rank vector bundle over a smooth finite dimensional manifold, and the section just needs to be C1, I think. And its unperturbed 0 set should be compact, right? So that should be. Which is true in our case. That's what our geometric things do. So we would like, some set of sections that, regularize the moduli space in the sense that, if you perturb now in the functorial way, right, and take the regularization, I should then get a compact manifold out. And if I perturb in two different ways, the compact manifolds I get should be cobordant. So far, so good. Let me cheat and take these things out for now here. But the first question here already is, well, so now I get all these cobordant manifolds, so I would like to define my fundamental class as, the fundamental class of these manifolds. But, well, this is an abstract manifold. It doesn't sit in any bigger space. Right, so the best place where I could think of this is maybe as, sitting in the dimension of, I'm expecting the virtual dimension, but it's just, sits in its own homology. Right, and what does this have to do with the homology of my moduli space, which is the unperturbed zero set regularized. So, let's see.
So is there any map from the perturbed zero set to the unperturbed one?
Not naturally yet. We'll see. I don't think we'll ever make one. So and I don't think there's a natural one. So the idea that we followed is a little different one. Well, so you would think some kind of projection.
Right, and you could push forward.
Or push, yeah.
But apparently projection doesn't.
Yeah, well, we'll see. This field is certainly open for more ideas. The present ideas, I think, are good enough to push the theory through, but not in a pretty way. So what would be pretty is the following. So this is complete dream land, which I'm going to burst that bubble pretty soon. But so, right, let's think of the base here. I would like to, I would like to cut out somehow my regularized moduli space. I would like to think of this as the zero set of a real section, of a map between spaces now, not between categories. Because I would like to have an ambient space. But I have all these little ambient spaces, the UIs. So how about if I manage to glue these together? The morphisms are somehow going to glue these together. Manifolds of different dimensions, not so clear how they get glued together, but something. At least there's a topological space. It's a quotient space, at least, that gives it a quotient topology. And I can do the same thing with these bundles here. And then the section does induce a map from the base to the fiber space, because it's supposed to be a functor, so it's compatible with morphisms. But you already notice that depending on which representative in the base you take, there are fibers of different ranks over it. So this is most definitely not even a vector bundle. So it's something ugly. It's a map between topological spaces. But if I add one of these sections to it that's also compatible with morphisms, I can think of a perturbed map. And I would like to somehow say that in some sense that's transverse to zero. If I then knew that this ambient space was locally compact and my perturbation was small, right, then I'd have some chance of saying that the perturbed zero set should be compact. That would be the neatest way of keeping things compact. So that takes care of the compactness. Let's do it this way. But for the manifold condition, yeah, well, certainly transversality should give me sort of a local homeomorphisms to Rn. So far, so good. But as I keep trying to point out, that a topological space also needs to be Hausdorff before it is a manifold. And I did convince myself second countability does come for free in this sense. But that's for the section of things you never thought you might need about concept topology. I'll try to get to. Right. But the main point here is there's really no good idea for getting Hausdorff property off this perturbed set, unless it sits in a Hausdorff ambient space. So that will be one of our tasks. Right? And then, once we have that, we have all these cobordisms, and then we could dream a little further and say, well, maybe this ambient space is not just locally compact and Hausdorff, maybe it's actually metric. And maybe it's metric in such a way that I can write my moduli space as the intersection of little delta neighborhoods of M bar 1. I think that is always true. Right, once that's a metric space, this is I can write this down. Right? And then I can run, well, if this is, I'm not sure check homology exists in all metric spaces. Actually, I think it does. Right. So once I have such a metric space, I could take my perturbations small enough so that they make the zero set sit in here. Right, the new less than some delta that depends on, less than some epsilon that depends on the delta. And then with that, we call this new subscript delta. My perturbed zero sets would have, so this is the black box that I talked about at the very beginning at some point. Check homology is the thing that works nicely together with limits in these metric spaces. So this is now a cycle that sits in this delta neighborhood, so it sits in this check homology of this delta neighborhood. And then I can take the inverse limit, so and define my actual zero set as the inverse limit as I let delta go to 0 of all the images of these cycles under the inclusion maps of delta neighborhoods into larger delta neighborhoods. Yes, I should write class of realization given by S plus. So this is the same kind of trick that I did when we had just the regularization theorem in finite rank bundles. Short of now understanding what check homology is, this is just sort of a black box that says, if you have a metric space and you can force your zero sets to lie in small neighborhoods of your moduli space, you can get into check homology.
Sorry, I don't understand how you're getting into check homology. You're using the fact that it commutes with the inverse limits or something?
Well, I'm using, I don't think that I can probably even say enough about check homology. So the one thing that I'm using here is that I have an embedding U into V, then I get, what is this? Which way do I go? Then the homology, the check homology of V.
Check homology.
Sorry?
The check homology, not the check homology.
Yes. Sits in check homology of U. simply because every cycle that sits in, oh goodness, it's exactly the wrong way around here. Okay. I want to say every cycle that sits in U then also sits in V. And this is not I don't know that even this is injective, but I have natural maps. Right. And so now what I have here is a whole lot of natural maps that the check homology of my moduli space all sits in, right? And I have cycles in each of them. Let me call this Z sub nu, Z sub delta. So, well, here, one thing I can say is, let's see. Right, here let's first sort of just choose a random sequence of perturbations that goes to 0 that give me a cycle in each one of these. And so then the question is, does that limit actually exist? Right. So one thing I can say here is that I have this cobordism property, right? And this cycle here I can map forward into here, and that perturbation nu delta prime actually also lives in the same space that this perturbation lives in, and if they're both in my correct space, then they're cobordant, and here's sort of equality here. And so that, and then I need some algebraic property of check homology that says when you have these properties, when you have cycles in each one of them, and always the sort of push forward maps, make them agree, then the inverse limit exists and is unique, and all cycles in the check homology of the limit you can get that way. Yeah, good, excellent. Right, and the caveat here is that this is with Q coefficients. Otherwise, I think there is a homology theory that was at least at some point developed by John Milner, that you could do this with Z coefficients. He was at some point our external advisor briefly and said, never mind. One reason being also that at the end of the day, of course, we want to apply this in a case where we only expect rational currents anyways from isotropies. Right, so that's our dream here. Right. That would be awfully nice. So that asks for a whole lot of properties of an ambient space. Not only do we want an ambient space, we want it to be a locally compact metric space. Well, let's see. So that was dreamland. So what do we actually have? So we have Kuranishi charts. So which I should write down more precisely again. And well, so each one Kuranishi chart is a section in a bundle and the embedding of a zero set into my moduli space, but into an open subset of that, which I want to give a name. So bunch of things happening here, right? So I have a lot of open subsets of my moduli space that cover it eventually, hopefully, right? So I want an open cover, to have sort of an atlas in the end. And these is what Huse and I started calling footprints. Really thinking that somehow the Kuranishi chart itself is sort of a ghost. It's hard to nail down. You don't ever really see it. It's like the Yeti. All you ever see is the footprint, which can be pretty big, but sometimes it's not so easy to, read it. Right. So then I have these zero sets. I would like my embeddings to be local homeomorphisms. Right? And these are manifolds. And here already somehow conventions can change. In general, this could be a vector bundle. Well, or you could ask your manifold to actually be an open set in Rn. So this is sort of the most general version here. What we usually, whenever I say Kuranishi chart next, what I really think is trivial vector bundle. So this will be U times E. Right? And this is the one time where I actually want to say what a Kuranishi chart with isotropy is. That's when all of this is equivariant under a finite group action. Oops. And instead of the zero set, I embed the zero set 1 for group. So, and then that just means I have to, in the end, add these groups to my morphisms. But I'm not going to do that. It's going to be hard enough as is. And I argued that you can get these guys, analytically everywhere, and so, that hopefully, we defined our Gromov topology on our compactified moduli space so that the footprints you get are open, and so you can then cover, assuming that our Gromov compactified moduli space is in fact compact, you could cover it with finitely many. That's the good news. But then, I hinted at some point a little bit is how you get transition maps, and now is the...
So is it that S is just any random section?
Yes.
And then we're attaching to it, or as an extra piece of data, some map that represents the zero section as some open set of the module?
Right, yes. Yeah, you particularly, right, what you do want to think of is, you want to think of S as very irregular. Right, so...
Does that already imply some sort of control on what the zero set is then? If it's going to be kind of like embedding as an open set in the moduli space?
Yeah, but it's an open set of a moduli space of the zero set of a function on Rn. Smooth function, but utterly non-transverse. So, So here's the examples that I tried to make. Well, not nearly as ugly looking as they actually are in real life. So each of these here, each of the bases, so this is my Ui, and that's my Uj. So both of them are nice open sets in R2. That's the gray squares, right? And then both of them have, trivial fibered vector bundles over them, which, let's see. Let me say maybe these are two-dimensional even, right? So I really just expect a zero-dimensional zero set. But what I drew here, if you think of this as all having the same color, that's my zero set. So this is and I was gonna. I think color coding will be very helpful at this point. Oops. This is what I'd like. Orange. But the smartbot doesn't like that. What about pink? Oh, pink is okay. Orange is okay too. Okay. And there's a green bit. This green bit is what I want to think of as the overlap of these two charts. Yeah, it looks sort of homeomorphic. So I want to think of the two footprints in my moduli space. That's this green stuff. And they now sit in each of these by pullback. Right, so here, if I pull back with psi I, the fj, then I get this green bit, and here if I pull back with psi j, the fi. So, yeah, but different kinds of crazinesses happen in both of these charts because they, cover different open subsets in M bar. So the piece of structure that we have are these local embeddings, and we really only have, so the natural induced transition map is really just on the footprint. So this map here is my psi I and then psi j inverse. So that's a pretty weird structure, right? And that certainly doesn't give us a decent, I mean, you could now try and take all your UIs and sort of glue them together just on the zero set. But that would mean you glue them together maybe on this two-dimensional subset and then just sort of on the one-dimensional and on some more fuzzy things. That just seems wrong. So what we would really like, our dream is that somehow this coordinate change should come from a coordinate change between the ambient, the fattenings. So I'd like, and ideally my moduli space would sit in some big ambient space so that, I make the fattenings in that big ambient space and then maybe have an overlap in there. So, can we pull that off? So that way we would have transition maps between open subsets, and we can weaken that dream a little bit here, right? It doesn't need to be the embedding of all of UI, and I also don't maybe necessarily need this big ambient space, so let me try the slightly refined thing here. So maybe I have an open subset for each j in my UI, so that that is homeomorphic to an uji in my uj. And that should of course be made so that when I look at the zero set here and intersect it with that open set, that should be exactly the green stuff. That should be exactly my footprint in here. And the given transition map here should be extended by this bigger open map here. Right, so this involves choices of open sets in here, on which I'd like to make my transition map.
But in particular, we don't need the intersection of two footprints to be a footprint.
We don't necessarily need that. I think the only way we've figured out how to get it is to make that.
So that's part of the assumption?
Not yet.
Okay.
We'll get there.
So how important is it that you extend your transition maps that are defined on U and not just on footprints?
Well, if you don't have transition maps on open sets, well, right, okay, well, what happens, right? So you go into this chart, you perturb your section a little bit, you get a perturbed zero
and they
set.
have like no relation to one
That's
another.
going to sit a little bit off
Yeah,
this.
right.
I don't think you can perturb and keep the perturbed zero set within the unperturbed zero set.
Right.
Right? So if you smoothen this out, it's going to get pushed off. You can probably keep it in a small open subset around the zero set,
That's
but
all.
you need some way of relating the perturbed things. So yeah, yes. So quite central, I think. Yeah. I mean, of course, one could dream of a theory that sort of keeps the perturbed zero set in the zero set. So it's not obviously wrong. Well, I think it's wrong, but I'm going to have a hard time making a counterexample. But you would need some sort of fractal zero set that's cut out not transversely, and then somehow, a zero set that wants to have sort of the same dimension, but if you try to put it in, it's going to be forced to not be differentiable. It's an interesting world to try and construct counterexamples in. So, all right. So, same picture again. I'm trying to construct this a little more specifically. What do we actually get from the analysis? So, this is the recap here of what my charts are. And before I write down how we actually constructed them, here's that transition map between the green stuff again, and what we're now thinking is that we'll find some fattening, that's the purple, into open sets. That I've very carefully intersected the zero set exactly in the green stuff with this dotted purple sets. So those are my little fattenings here. And these are the things that we're going to, I'm not going to be able to map between them directly. What's going to happen is that I'm going to be able to embed both of them in a bigger space. That's a sort of a natural idea, I think, just on the level of categories. That has some named equivalence of categories where you don't have a map between the categories, you just have a factor into a common refinement. But in our case, this is going to be coming quite naturally from the analytic definition of these things, which is, so let's see, what is my, here's what, let me write this out here in this example. So in order to make, we made these finite dimensional reductions in a certain way. Right. Namely, we chose slicing conditions to, stabilize the maps, to sort of fix the parameterization, and then we chose some stabilizations to cover the co-kernel. Right. And we needed some small, open sets in some Sobolev space that made sure that, that's my open subset in which I sort of vary the maps so that they still intersect the slicing conditions transverse. So the model for these little fattenings were then sort of the stabilized, perturbed solutions of the d-bar operator. Right, so where d bar u is e. Right, so in particular the holomorphic ones are in there when e is 0, and so u is in this little domain ui and curly u, and e is in my vector space ei. And in order to fix the parameterization, I asked u at 0 and 1 to go through some fixed hypersurface, which it's called G0 and 1 here. All right. And my J's chart here works exactly the same way, except I have a different stabilization and different slicing conditions and a different neighborhood. So that's this guy over there. Right? And so you realize, these maps here are all close to some map and some parameterization and satisfy, something with this slicing condition. It's not clear how I would even get directly here. Can I if I reparameterize these? Sure, I can satisfy the slicing conditions, but I would need to know that these stabilizations Ej come from or are related to the Eis, because if I push it forward, it's going to satisfy some other perturbed bar equation. And presumably I've just covered my whole moduli space with some random choices of these that were not related. So the idea is to make something called a sum chart where I use the product of these two, at least stabilizations. But so when I do that, well, you can try a number of things. You'll end up realizing that it's best, to not try and sort of throw these marked points in and relate them directly. I'm just going to keep track of these two marked points and those two separately, which gets me into actually having to deal with tuples of marked points. So this is going to be a fairly large set of pairs UEF and marked points that have to do with the stabilization conditions. That's what I call little g and little h. So where? Okay. So U is still a map that's now holomorphic up to, somehow both E and F. In what sense is to be discussed. And my map U, I would like to go through all these hypersurfaces at the appropriate mark points. So far so good. Since I haven't fixed where these marked points are, I now have a lot of freedom of reparameterizing this. Right? So I can reparameterize this by composing U with phi, while doing something with the stabilizing vectors E and F, right, and pulling back with phi inverse of these mark points. That's now a quotient space here. And it looks like a quotient space that I get from a perturbed d-bar equation with slicing conditions. So analytically, that's not exactly a happy place to be. But I can, make this okay analytically. So this chart I need to actually sort of construct as the zero set of a Fredholm section. One way I can do this is I could just decide to fix the parameterization, by fixing these 2 points to be 0 and 1. Or I could fix h0 and h1 to be 0 and 1. Right. So that would fix this parameterization. And then this looks very similar to these kinds of equations, right, where I just have some extra mark points floating around and some not quite so understood bundle yet. But yeah, so something is doable. What is the beauty of this is that because I can construct this in different ways as the zero set of a Fredholm operator, I can also embed these guys in different ways. So the idea here is to construct this by fixing the first two mark points. And once I have that, I could make my embedding here. So that's my, that's the purple guy here. Right, I would like an open subset in here, potentially the whole set to embed in here. And I can do this by copying the U. I should probably take the E. Then it sort of already satisfies something like this, so I can take f equal to 0. Well, it does satisfy the slicing conditions at 0 and 1. And then I just need to read out where U intersects the hypersurfaces H. So sort of U inverse of HI. Right, of course that's a little fuzzy, right? But this is an element in here. So I just have to worry about making sure that I chose my domain. So right, actually here you can understand why I have to choose a smaller domain, right? Presumably I'm somewhere near the overlap, so I'm maybe I'm at a map which actually after some reparametrization sits in the other chart also. So after reparametrization it intersects these hypersurfaces H transversely. Right. Which means if I change my map here just a tiny little bit, it's still going to intersect H transversely. And that's what I need in order to be able to sort of read off these extra marked points here with, in an analytic, meaningful way. Question.
So the in the big space on the bottom line that you're embedding the upper left.
Right.
So the quotienting out is by homomorphism of the domain?
Right. Yes.
Okay, and okay, so we're assuming that we don't have any isotropy, which is why we get an embedding of the upper left thing.
Right. Yes.
And so the reason that the bottom thing isn't automatically already a Fredholm construction is because of the quotienting out.
Correct.
Is that right?
Yeah.
Okay.
I mean, there's two things happening here. I haven't told you. Even the map that takes U and evaluates it at a marked point is not smooth if you're on a Sobolev space. You can make it CK, but you have to worry a little bit about what context this actually is differentiable. So this is a little bit questionable, and then also what is this sum construction here? That's needs to be done, and
But even if those two things weren't issues,
even then then you would need to prove that there are two ways of giving this a smooth structure. One would be to give this a smooth structure and then prove that the automorphisms act smoothly and freely and properly.
right?
Right? So this is sort of equivariant transversality. Or, you take this other kind of description. Yes, right. However, if you do this other thing, then of course you need to make sure, right? So this gives you some smooth structure, and you'd better make sure that that smooth structure on this sort of fattened ambient space is equivalent to the smooth structure that you'd get from doing the same thing here, except fixing the second two mark points as 0 and 1. So, but what happens here is that you're reparametrizing on a finite dimensional space of maps that hopefully you've made all smooth, and so then reparametrization does act smoothly. And so that's the reason we expect this to actually be okay. So fattening seems to be the natural thing, because you have marked points that you want to sort of all throw into one set, and you also have different perturbations that you want to both allow. So that means what we have here. I'm going to summarize this mess algebraically. Right? What we did is, we kept all those choices here, right? And then we had to do some extra choices. We had to choose sort of little extra spaces that give us the neighborhoods here. Goodness, right? So these are the ones in which either this guy lies here, this would be in, right? I would need some little W1P neighborhood, and that's this curly U here. In the I parameterization, where I have that, and then in the J parameterization here, I would have curly U would have to lie in the curly UJ. Also a little W2P neighborhood or something. Right, so choices of neighborhoods. And then, what is this sum about? Right? Between these two charts here, there's a transition map, of our favorite form, and I need to be able to pull the stabilization EJ back to here, to get somehow a stabilization of my D-bar operator. In particular, would be nice if that was somehow a C1 bundle with C1 sections. And I need the same thing on the other side, because if I want to make this description here, with a smooth structure, I need to be able to push this bundle forward. So, and that's something that happens in the infinite dimensional context, right? Because you need to talk about this here as a Fredholm problem. And so in the infinite dimensional context, that map is not C1. So that's why you need special stabilizations that will do that job.
So kind of confused. So the point of it is we need to form E plus F.
Right. Yes.
And so isn't the point that we need to sort of push EI and EJ down to the bottom thing rather than pull anything back?
Let's see. Right, so let me try to just sort of sillily write this. So I have this big domain UI in which I take a small domain UI I of things that are also transverse to the H's. So these here are transverse to the G slices. And so now what I want to be able to do is want to be able to map U to no, hold on. What do I want to do? This. So I would like to be able to make sense of the equation d bar j u equal to E at U plus F at U, where E is a section of EI over this big curly UI. But F is a section over the wrong space, right? So that means this is not a good thing here. I need to take this reparametrization here. And so I should take F at the point that I get from reparametrizing U so that it sits in that slice. So, right, pretty much, so this is now my map here. This should be a Fredholm operator, from W, say 2p to W1p. Right. The problem is, this E and F can be as smooth as they want. If I compose them with a not differentiable map, it's not so clear how differentiable that's going to be. So, the now let me not try to write this down. There is some special form of these bundles in which this right-hand side, if you write it out precisely, looks better. And you can sort of push the lack of differentiability a little bit into the mark points. And so then you're only losing k-fold differentiability and not first differentiability, I think.
And that's what you end up doing.
Yeah. So things are doable there, with a little sweat. Somehow the frustrating realization for me, though, was that you can't deal with very abstract things here. You need a geometric idea of how to make this better.
Oh, like pushing it to the mark points.
Right. Yes. Yeah. This has something to do. This summing. Well, the only way we figured out how to do was to use something called the universal curve, where you start thinking of your holomorphic maps U again as more submanifolds of some big space, not as solutions to PDE. So you take, just like with wiggling with the J, you end up taking perturbations that really come from perturbing the geometric problem and not so much the analytic problem. All right. Good. So, so there's bad news that this is not all so easy, but the good news is this: once you've written down your finite dimensional reductions, sort of only a little bit more choice of open sets in the Banach spaces seems to induce some kind of embeddings into a bigger thing. So let's make that precise with a little less fuzz around. So again, I have a whole bunch of what we're going to start calling basic Kuranishi charts. And these are the ones that in first go cover my moduli space. And then here's a diagram of how they are related. So this is the I's chart and the J's chart, right? And for each of them I have open subsets that embed into a bigger thing. And my bigger thing actually had, secretly this extra stabilizing bundle that was the product. And the d-bar operator secretly is the section here. So what I get here is sort of two part transition data. One is this orange bit, which is an extra Kuranishi chart, and then the purple things is what we call coordinate changes. So my sum charts then happen here I just had an overlap of two charts. In general, I could take any subset of my n charts that cover my moduli space. And when is it that I need an overlap? It's when the intersection of all the footprints is not empty. And now one could sort of define a weaker notion, but to answer the question before is, does the intersection of the footprints have to be a footprint again? I believe one can always make it so. Right? So this sum chart for some subset here now. So not only are we taking the sum of the stabilization of each of the single charts, we're also claiming that the zero set is actually going to cover this entire footprint. Or it's going to cover the entire overlap. So that seems to be naturally possible, from the analytic description that I did there. So this here you could also write as now the footprint for the subset capital I. And there's this nice property here that the sort of the sum chart actually has the sum of obstruction spaces. This is what in our first paper we called additive. Gives you some nice control.
So you're assuming there's finitely many footprints?
Yeah, because why not? My moduli space is compact. So if I start with finitely many basic charts, I get finitely many subsets, finitely many intersections. I've now added a whole bunch of charts, that cover all these intersections. But the nice thing is now I'm in a situation where I only need to think about coordinate changes for inclusions of footprints. Right. So I'm only going to need coordinate changes when one of these i's is a subset of j, which is exactly meaning that the footprints are contained in each other. Right. And then there's a lot of ambient structure that I don't need to construct. So I have my two sum charts now, right? And there's the one core choice that needs to be made is the choice of this open set in here. That had something to do with the choice that comes from the choice of WKP neighborhood, so that the slicing conditions are okay. And then there's an embedding here that gets constructed by the analysis. Here is, again, somehow our notation has already evolved here. These obstruction spaces here have, natural splittings now. And since I is a subset of J, this sum here sits naturally in there. Which in our first paper we called phi hat ij. So with that, this is all one big commuting diagram in two different directions. The bundles commute, they automatically commute simply because these are trivial bundles, right? But the sections particular have to be intertwined. Right. Question.
So do you have to worry about some kind of coherence when you're choosing your UIJs?
Yes, good question. This is about coming up. Yes.
Okay.
Right, because so far, let's think about this for a second here. Let's say I was trying to define a manifold. I could do this by setting all my obstruction spaces, or the e's, to just 0, right? And set my sections equal to 0, then I have a whole bunch of manifolds, and they all embed into my ambient space, or into my moduli space, right? Which is compact, metric, Hausdorff, fine, but now, I've covered it, but I would like to say what the overlap is, how they, relate. And of course, in that case, I get the full transition map induced. But I want to somehow describe this manifold now just without knowing it as a topological space, just by taking these zero sets and gluing them together with my transition maps. Right? And I don't know whether you've ever seen that definition of a manifold. There is a cocycle condition. Right? So in this case, the cocycle condition would simply say that if there are two embeddings that you can compose them and they're equal to the direct transition map.
That doesn't say anything about UIJs, because that
Not yet, right.
Oh, okay.
Right, so if there was no obstruction spaces, then this would be the entire cocycle condition. Because this would have to hold on the domain where both are defined, and it's sort of, there's only one way of saying the cocycle condition, and that's in the setting for manifolds. But, right, in our setting now, because you have the, let's see, how do I say this? Right, for manifolds, each of these phi's actually really comes from the transition map through your total space. So there's no choice involved there. You know, here we have this choice of the fattening open set. Right, so there's a choice here. And so there's different ways of saying cocycle condition, and what we construct naturally is something where these two embeddings, or the composition of embeddings, is equal to the direct embedding when both of them are defined. So I haven't tried to make an example of this, right? But you know, in general, really, there's no reason that one or the other will have a larger domain. And that's exactly where, well, you know, this is what you have naturally, analytically, because you make all these choices of ambient spaces. That's not, you know, sort of organized in any sense usually. But, right, so we wanted at least a category so we could talk about compatibility as in a functorial way. And so in a category now, right, so what is my category going to be? Right? So, well, these were my objects here, and clearly my morphisms somehow should come from these little open sets and the embeddings of the phis. So, let's see. Let me take my morphisms. Well, so I need identities first. So I'm going to start with a copy of the objects. And I'm going to call U capital I, just this one. You know, with the trivial transition map, that's just the identity. And then I'm going to add all the I not equal to j QIJs. That's here, and I need to now make source and target maps, right? So source is just my embedding into the UI. Oops. And the target on each of them is my phi ij, embedding into the uj. So map T. Well, right. Note this is not going to be a groupoid, because groupoid would mean that I would have to invert these embeddings phi ij. And they would then not be defined on open sets, but on, at best, submanifolds. Don't try. We'd rather not do that. Right? But I'd like a composition to be defined here, right? This is a category. I ought to be able to compose morphisms. So what does that look like? More times more to morphisms. Somehow I have a situation where, let me try to get this right. Right, so there's a uij, this is my first piece of morphism space, that gets embedded into uj, but then there's just an open subset of uj, that's ujk, that gets embedded to uk. So that's the somehow two-step composition. That's this left-hand side here. And the right-hand side somehow comes from a direct composition where I have a uik subset in here that goes directly there. So in order for composition to even be a well-defined operation on my category, I need the composed map to be defined whenever the two single ones can be composed. Right? So the left-hand side makes sense if I'm in the pre-image of ujk, and so the condition for this to even be a category is for this pre-image to lie in the domain of phi ik. Right? So that's the honest co-cycle condition that gives us a category. But, right, so category now means we can talk about the realization. Right? So we can take the object space and quotient by the morphisms. And when you then ask yourself, well, when is that bugger even Hausdorff? Well, you need the equivalence relation to be closed or proper, right? And so you need some control on how these things get glued together, and we got this control from something called tameness, which I'm going to try to actually, I don't think I can explain that really very well. I'm going to just give you a feeling of what that notion is. It's a lot stronger than the strong co-cycle condition, but in particular it applies the strong co-cycle condition. Namely, that says that not only do I have this equality, not only is composition well defined, but the composed guy exists if and only if it is, a direct morphism from I to k if and exists if and only if it factors through j. Right? So the algebraic identity needs to hold together with an identity of domains. Sort of makes sense in the way if you think about somehow limits of morphisms existing. Yeah, you'd like some more handle on them. So, but you can hopefully also imagine that if you just started with this random number of choices and you're trying to get all of this control here, there's two open sets here that are involved as written, but really it's three open sets because it also the domain of phi ij is a choice here. And so there's no clear induction direction in which you could make this refinement. So this is when you need collaborators who were point set topologists at some point and can just write down some crazy inductive refinement that really sort of the first thing we managed to prove at some point was that under this extra additivity condition, you could somehow take something with a weak co-cycle condition and just sort of keep throwing things out of these uij's to eventually get a strong co-cycle condition. And I have no reason why that should be true, other than the fact that I think we proved it, which is really not a good sign for a theory. Usually you should have some overarching reason for things working. Yeah. And I think this is the first shade somehow of a sheaf theoretic theory, really. I'm pretty sure that this kind of refinement actually has some sort of equivalent in some language of sheaves, being, but somehow make compositions of in a sort of some kind of chain complex theory Right. So, but that might be giving us a Hausdorff space. What about local compactness and things? So, yeah, we should dream of ambient spaces, and we should dream of a Hausdorff ambient space. But the rest we really shouldn't think of, and that's going to be fun in point set topology. So the classical nightmare example is going to be a very simple one. The simplest one you can think of when you embed, manifolds of different dimension into each other. 1 into 2, and here the thing is that I'm not embedding my entire base chart UI, I'm just embedding an open subset. And so that goes into some two-dimensional bit. There I've even gone all the way through, because really in practice, actually what this set is that's going to be this part of the additivity says that this set is actually the image of this embedding here is going to be closed in UJ, because it is exactly the space where the section isn't 0, but it takes values in the subspace EI of EJ. So that's good news. We can actually understand the images of our morphisms in an analytic way on the subset itself. But everything else now goes wrong. So if you try to glue these things together with the quotient topology, then I'll go through this on Wednesday. But the painful fact is that, of course, as you draw this looks like a subset of R2 or C. But the topology that you're putting on, that says a subset up here is open if it's pre-image and both of these things is open, is very much not the ambient topology from C. And the one really troublesome point is that 0 point that sort of sits in UI, but it doesn't quite sit in UJ. And what I'm going to see is that that's not locally compact, which you can sort of imagine. The sort of the red point is in here, but its neighborhoods somehow in the UJ and don't look terribly compact. But not only that, it's also not first countable, so I don't find a countable generating set of domains of neighborhoods of the 0. And that means it's not metrizable. And that's really weird. That's something that we proved that this was metrizable a number of times, until we realized that the counterexample was staring in our face. So these are things we shouldn't dream of, and then we have to think of other ways to get our space to somehow control compactness of our perturbed 0 sets, and to also there's a question: do you need a metric or not? We make a metric on something, but it's not the whole ambient space. Right. So nightmares in topology on Wednesday, and and then we can go back to I think this is part of the sort of playoff between do you want to have nightmares about analysis or nightmares about topology? So I will then have presented both to you, and then you can choose which nightmares to live with.